Welcome back. In the last lecture, we discussed the selection of inside design conditions based on the comfort criteria. In this lecture, I shall discuss the selection of outside design conditions and then selection of supply conditions based on the psychrometry of air conditioning systems. So, the specific objectives of this particular lecture are to discuss criteria for selection of outside design conditions, discuss selection of supply conditions and psychrometry of air conditioning systems, analyze summer air conditioning systems, namely simple system with 100% recirculated air, system with outdoor air, then system for high latent load applications. At the end of the lecture, you should be able to select suitable outdoor design conditions based on weather data and applications, find the supply conditions based on the psychrometry of air conditioning systems, and analyze various summer air conditioning systems. So, first let us look at how to select outside design conditions. So, the ambient as you know very well, the ambient temperature and moisture content vary from hour to hour and from day to day and from place to place. For most of the major locations of the world, meteorological data are available in the form of mean daily or monthly maximum and minimum temperatures and corresponding relative humidity or wet bulb temperature. This data is recorded and it is available. Now, selection of the worst possible conditions lead to excessively large cooling or heating equipment, as worst conditions prevail only for a few hours in a year. That means, if you look at the meteorological data and if you select the worst possible condition, that means if you are designing a summer air conditioning system, you take the maximum possible temperature, dry bulb temperature and maximum possible wet bulb temperature and do the cooling load calculations, and if you decide your capacity of the cooling system accordingly, then you will find that the installed capacity is really excessive, because the worst conditions generally prevail only for a few hours throughout an year. Okay, so it is not really economical. So, there must be some other criteria for fixing the outside design conditions. So, let us look at these criteria. First, let us look at outdoor design conditions for summer. Outdoor design conditions for summer are chosen based on the values of dry bulb and mean coincident wet bulb temperature, that is equaled or exceeded 1%, 2.5% or 5% of total hours from June to September. From June to September, the total number of hours will be about 28, that means 2928 hours. So, what it basically means is you have to select, let us say that I am selecting 1% value. Okay, that means 1% of the time the outside design conditions will be higher than the selected condition. Okay, 1% of 2928 is roughly about 30 hours. Okay, so only during 30 hours the outside conditions will be hotter and humider than the selected conditions. Okay, that means the system capacity may be inadequate only for 30 hours in 1 year. Okay, if you are selecting, let us say 2.5% data, then for 75 hours the system capacity will be slightly lower than required. Similarly, for 5% data it will be about 150 hours. The outside design condition will be slightly more than the selected conditions. Okay, so this is the meaning of selecting the outside design condition based on 1% or 2.5% or 5% value of the dry bulb. And one more thing you have to notice here is you are not taking the maximum wet bulb temperature, you are taking the coincident wet bulb temperature. That means, what is wet bulb temperature? When the dry bulb temperature is at 1% value or 2.5% value or 5% value. Okay, this is the criteria suggested for selecting the outside design conditions. These values for major locations in the world are available in data books. For example, ASHRAE data book gives the 1% value or 2.5% value or 5% value for major locations in the world. And in the absence of any special requirements, ASHRAE recommends the 2.5% value for summer outdoor design conditions. So, special requirements means there are some situations where the inside temperature is very critical. That means, even for 10 hours of the throughout an year, you do not want the temperature to exceed a particular comfort value. Okay, that means inside condition should not exceed a particular value under any circumstances. Then you have to go for a 1% value instead of going for a 2.5% value. On the other hand, there are some applications where the temperature is not so critical. Okay, 2-3 degrees variation is allowed, then instead of going for 2.5%, one can go for 5% value. Okay, so thereby you will be saving the system cost, okay, both install cost as well as the running cost. But in the absence of any recommendations, one can go for the 2.5% value. Okay. Next comes the selection of outdoor design conditions for winter. So, just like summer, outdoor design conditions for winter are chosen based on the values of dry bulb temperature that is equal or exceeded 99%, 97.5% or 95% of total hours from December to February. December to February is a typical winter time. So, if you count the number of hours, you will find that from December to February there will be about 2160 hours. So, if I am selecting, let us say 99% value, dry bulb temperature value, that means 1% of the time, I mean that means 1% of 2160 hours, that is about 21 hours, the outside temperature will be lower than what is required. Okay, that means your heating system will be inadequate for 1% of the total duration of 2160 hours. Similarly, if it is 97.5% means 2.5% of the time the outside conditions will be lower than the design condition. That means the system capacity will be inadequate only for 2.5% of the time. Okay. So, this is how the winter design conditions are fixed. Similar to summer design conditions, winter design conditions are also available in data books such as ASHRAE data books. Okay. And generally the 97.5% value is recommended if there is no special special requirement exists. But if the building is made of lightweight materials, if the building is poorly insulated, or if it has considerable glass, or the space temperature is critical, then the 99% value is recommended. Okay, so when some special situations exist, then we can go for 99% value. 99% value means the installed capacity will be slightly higher than that of 97.5% value. Okay. Now, let us look at the psychrometry of air conditioning systems. From known cooling and heating loads on the building and design inside and outside conditions, psychrometric calculations are performed to find supply air conditions. By supply air conditions, we mean air flow rate, that means mass flow rate of the supply air, what is the supply air dry bulb temperature, what is its humidity ratio and enthalpy. All these are known as supply air conditions. Second thing is we can also find out the coil specification, that means what is the latent and sensible loads on the coil, what is the coil required coil ADP, that is apparatus dew point, and what is the required coil bypass factor. Normally, depending upon the ventilation requirements of the building, the required outdoor or fresh air is specified. Okay, this is something which is specified based on the ventilation requirements. Now, let me show a typical summer air conditioning system. Okay, this can be any air conditioning system, but let me take the case of summer air conditioning. In summer air conditioning, let us say that the required inside conditions are say 25 degrees centigrade, and required humidity ratio, let us say, is 10 grams per kg of dry air. Okay, and the enthalpy is a corresponding enthalpy. Let us say these are the required inside conditions which correspond to our comfort requirement. Since it is summer, outdoor conditions will be hotter and humider. That means let us say that outside temperature is 35 degrees centigrade and outside humidity is, let us say, 30 grams per kg of dry air. Since outdoor temperature is greater than inside temperature, outside humidity is greater than inside humidity, there will be, and the building is not perfectly insulated, so there will be sensible heat transfer from outside to the inside of the building. There will always also be latent heat transfer from outside to the inside of the building. Okay, this could be a single room or it could be a huge building consisting of many rooms, right. So, we want to maintain the inside conditions at these values and there is a continuous addition of sensible as well as latent heats to the building. So, to maintain the room at these particular conditions, we have to take out this heat at the rate at which it is entering into the conditioned space. This is achieved by using an air conditioning system. In the air conditioning system, what we do is we supply, for this case for example, a supply air which is cold and dry. Okay. So, cold and dry at the required mass flow rate is supplied to the building. This cold and dry air flows through the conditioned space, and as it flows through it, it picks the sensible heat and it picks the latent heat, and we assume that when it comes out of the building or comes out of the conditioned space, its conditions will be almost same as the conditioned space conditions. Okay. So, what enters into the conditioned space is cold and dry air, and what comes out is relatively warm and humid air, okay, at the same conditions as that of the conditioned space. That means at 25 degree centigrade, and let us say, and the humidity of 10 grams per kg. Okay, so at this condition the air comes out. Now the air flows through the ducts. These are all the ducts, the lines. Okay, and some part of the air is thrown out, that is exhaust air is thrown out, and the rest is recirculated. This is the recirculated air. Now this air is thrown out because we continuously want to add some outdoor air to cater to the ventilation requirements. Okay, so we supply some outdoor air. So at this point, this recirculated air and outdoor air may get mixed, and you have a mixed air here, and this mixed air is quite warm and humid. Okay, so it has to be made again cold and dry. So it is made to flow through a cooling coil. As it flows through the cooling coil, it rejects sensible and latent heats to the cooling coil, and in that process the air becomes cold and dry. Okay, so this cold and dry air is again supplied to the building. The cycle continues. Okay, so ultimately you see that the building at the building you have latent and sensible heat transfers to the conditioned space, and the air is picking up these heats and it is rejecting that heat to the cooling coil. This cooling coil could be the evaporator of a refrigerant system. So the refrigerant evaporates, and ultimately this heat is rejected to the ambient at the condenser. Okay, so this is a typical summer air conditioning system. Okay, and the psychrometry, we do perform the psychrometric calculations first to find out what should be the required mass flow rate of supply air. Okay, what is the required mass flow rate, and what should be its temperature, and what should be its humidity ratio. Okay, so all these things we will have to fix by performing psychrometric calculations, right? And we also have to know what should be the required cooling capacity of the coil. Okay, how much sensible heat has to be rejected at the coil, how much latent heat has to be rejected at the coil, what is the required bypass factor of the coil, and what should be the coil ADP. Okay, that is apparatus dew point. Okay, so all these things will be obtained by performing the psychrometric calculations. Okay. Now let us begin with summer air conditioning systems. First, let us take a simple system with 100% recirculated air. So, okay, let me first describe the system. So, as I said, this is a simple system with 100% recirculated air. That means we are not throwing any air, nor we are adding any outside air. So, the same air is flowing through the system again and again. Okay, you can see that it is a closed system as far as air is concerned. Okay, again you have the sensible and latent heat loads on the building. This is the I, the conditioned space state, and let us say this S, the same as this. This is the state of the supply air, and the state of the air at the exit of the conditioned space is same as the conditioned space I. Okay, and if you are assuming that there is no heat transfer in the duct, and if the fan power is negligible, then you find that at this point, that means at the inlet to the cooling coil also the conditioned space conditions exist. That means you have the air state as I itself. So, in the cooling coil it undergoes cooling and humidification. So, at point S you have cold and dry air, okay, and the same cold and dry air goes to the building. So, we have a supply fan here. You may also have a return fan. Okay, return fan is an option, and as I said, all these lines are the ducts through which the air flows. Okay, and the same process is shown on a psychrometric chart here. So, you have the dry bulb temperature here on the psychrometric chart. As you know, on the y axis we have the humidity ratio, and this, as you know, is the 100% relative humidity or saturation curve. Okay, and point I is the state of the conditioned air in the inside the building, and point S is state of the air at the exit of the cooling coil or at the inlet to the conditioned space. Okay. So, as I said, cold and dry air is supplied to the room, and the air that leaves the conditioned space is assumed to be at the same conditions as that of the conditioned space. The supply air condition should be such that as it flows through the conditioned space, it can counteract the sensible and latent heat transfers taking place from the outside to the conditioned space. so that the space can be maintained at required low temperature and humidity. I have explained this already. Now, assuming no heat gains in the supply and return ducts and no energy addition to the fans, energy addition due to the fans, and applying energy balance across the room, the different loads on the room are, okay, so let us look at the room. What we are doing is taking a control volume, let us say I am taking a control volume, okay, and if you are assuming a steady state and if you are applying energy balance across this control volume, you find that the rate at which the sensible heat is entering into the building must be the rate at which it is leaving because of the airflow. That means Qs R should be equal to supply airflow rate into CPM, that is a moist air humidity specific heat of the humid air into Ti minus Ts. Okay, this is the energy balance for the sensible heat portion. Similarly, you can perform an energy balance for the latent part, and you can also perform an energy balance for the total heat transfer rate. Okay, so that is what is done here, and you get this kind of equations for the sensible heat transfer rate. This is the equation. QSR is a sensible cooling load on the building. Okay, S stands for sensible, R stands for the room or building. That is equal to MS, where MS is the supply air mass flow rate, CPM as I said is the specific heat of the moist air, Ti is the conditioned space temperature, Ts is the supply air temperature. Similarly, the latent load on the building QLR, that is equal to mass flow rate of the supply air MS into HFG is the latent heat of vaporization, multiplied by humidity ratio difference. Wi is the humidity ratio inside the conditioned space, Wf is the humidity ratio of the supply air. Okay, so these two are for the sensible and latent heat loads or sensible and latent heat transfers. Similarly, you can write an equation as I said for the total heat transfer rate. Total heat transfer rate QTR is nothing but sensible heat transfer rate plus latent heat transfer rate. So, that is nothing but mass flow rate of the supply air multiplied by the enthalpy rise of the air as it flows through the conditioned space. Here Hi is the exit enthalpy of the air and Hs is the inlet enthalpy of the air or supply air. Okay. And the room sensible heat factor, as you have seen, RSHF is simply defined as the ratio of the sensible heat transfer to the total heat transfer. Okay, QSR divided by QTR. Now, from the RSHF value, one can calculate the slope of the process line undergone by the air as it flows through the conditioned space. That means slope of this line. Okay, let us say if this is theta. Okay, the tan theta is the slope of this line. This we can obtain if we know the RSHF or the sensible heat factor. This we have discussed in the last lecture. Okay, and we have seen in the last lecture that the expression for the slope is given by this value, that is tan theta is 1/2451 multiplied by 1 minus RSHF divided by RSHF, where RSHF is the room sensible heat factor, which is known to us. Okay, and one very important thing to be noted here is that for the given room sensible and latent cooling loads, the supply condition must always lie on this line so that it can extract the sensible and latent loads on the conditioned space in the required proportions. That means we know the, as I said, let me quickly repeat what I said. We know this conditioned space state I based on the comfort criteria. This is known to us. Okay, so we can place this point on the psychrometric chart, and the slope of this line can be obtained if you know the value of RSHF. Okay, for the time being, let us say that we know the latent and sensible heat loads on the building, right? So we can calculate RSHF, and from RSHF we can find out what is slope of the line. Once you know the slope of the line and this inlet state I, then you can draw this line. Okay, this RSHF line, and the supply air condition must lie somewhere on this line. Okay, it cannot lie anywhere else. If it is lying anywhere else, then it cannot take the sensible and latent heat loads in the required proportion. Okay, so if it has to, if the air, this air has to take the sensible and latent heat loads in this required proportion, then this must always lie on this RSHF line. Okay, so that is Okay. Now, since condition I is known, say from thermal comfort criteria, knowing the slope, one can draw the process line Si through I. We have already explained this. The intersection of this line with the saturation curve gives the ADP of the cooling coil. We also know this. If you extend this line, let us say that this we are able to draw this line. Okay, so we are able to draw this line because we know the slope of the line and we know one point. So if you draw this line and if you extend this line, where this line extend this saturation curve, that temperature will give you the coil ADP. Okay, ADP of the cooling coil. For the case of 100% recirculation, the process that the air undergoes as it flows through the cooling coil, that means process IS, will be exactly opposite to the process undergone by air as it flows through the room, that is process SI. Okay. That means what is happening for the air as it flows through the conditioned space, that means as it moves from this point to this point, will be exactly opposite to what is happening to the air as it flows through the cooling coil. Okay, that means process IS will be exactly equal and opposite to process SI for this special condition of 100% recirculated air. That is why you have a single line here. Okay. So, as the air flows through the room, the process will be like this, and as air flows through the cooling coil, the process will be like this. That means, as the air flows through the conditioned space, air picks up sensible heat and it also picks up latent heat. That means, its temperature increases and its moisture content increases. Okay, as it flows through the conditioned space, and the same air as it flows through the cooling coil, its temperature reduces and its humidity ratio also reduces. Okay, because that means we have to go for a cooling and dehumidification process in the cooling coil. Okay, so as far as the conditioned space is concerned, it is heating and humidification, and as far as the cooling coil is concerned, it is cooling and dehumidification process. And if you plot these two processes on the psychrometric chart, they exactly coincide. Only thing is that the direction will be opposite. Okay. Hence, the load on the cooling coil is exactly equal to the load on the room. Okay. That means this QSR is exactly equal to QSC. Whatever sensible heat is being transferred to the room has to be rejected at the cooling coil. Similarly, whatever latent heat is transferred to the room has to be rejected at the cooling coil. Okay, that means QSR is equal to QSC, that is coil load, and QLR is equal to QLC. Okay, this is not always valid. This is valid only for this particular system with 100% recirculated air. Now we have to fix the supply conditions. How do we fix the supply condition? The supply conditions have to be fixed from the equations for different room loads. What are those equations? We have three equations. One equation for sensible heat transfer, one for latent heat transfer, one for total heat transfer. And if you look at these equations, we know Ti, we know Wi, we know Hi. Okay, because these are fixed based on your inside condition space requirements, for example, based on comfort criteria. Okay, so these are known, and these will be estimated by performing cooling load calculations. Okay, this we will discuss a little later. For the time being, let us assume that we know these things also from cooling load calculations. Okay, so these things are known to us. Ti, Wi and Hi are known, and let us assume that CPM is also known to us, that is the specific heat is known, latent heat of vaporization also known. So what are the unknowns? Unknowns are mass flow rate of the supply air, temperature of the supply air, humidity ratio of the supply air, and enthalpy of the supply air. So there are four unknowns, Ms, Ts, Ws and Hs, and there are three equations. Okay. Since there are four unknowns and three equations, one parameter has to be fixed to find the other three unknown parameters obviously. So if bypass factor X of the cooling coil is known, then from the definition of bypass factor we know that for the cooling coil the bypass factor is given like this: X is equal to Ts minus TADP divided by Ti minus TADP, where Ts is the exit temperature of the cooling coil, that means exit temperature of air at the cooling coil, TADP is the apparatus dew point of the coil, Ti is the air temperature at the inlet to the cooling coil. Okay, so this is based on the definition of bypass factor. So from this equation you can write Ts is equal to TADP plus x into Ti minus TADP. Now, x is known to us, it is specified by the manufacturer, let us say. So, this is known to us, Ti is known to us, TADP we have obtained by extending the line and from the intersection of that RSHF line with the saturation curve. So, this is also known to us. So, we can find out what is the required supply temperature. Okay. So, once we know the supply temperature, then the mass flow rate of supply air is simply obtained from this equation, Ms is equal to QSR divided by Cpm into Ti minus Ts. Ti minus Ts can be written in terms of coil ADP and the bypass factor, that is Ti minus TADP into 1 minus x, right. And the supply air humidity ratio and enthalpy are obtained from the equations for the latent load and the total load. Okay. So, once we know this, this is known to us, this is known to us, this is known to us, this is known, everything is known on this side. So, we can find out what should be the supply air enthalpy, what should be the supply air humidity ratio. Okay. So, once we know one parameter, that is, let us say the supply air temperature, all other things can be obtained. Now, from the equation it is clear that the required mass flow rate of supply air decreases as the bypass factor x increases. That means, from this equation you can see that if everything else is fixed, as the bypass factor x increases, this also increases. Okay. In the limiting case, when the bypass factor is 0, okay, that means on the other side, when the bypass factor is 0, the minimum amount of supply air flow rate required is given by this equation. This is the minimum amount of supply air required, that is equal to sensible heat load on the building divided by specific heat of the moist air multiplied by Ti minus TADP. So, this is the minimum amount of supply air required. Okay. Thus, with 100% recirculated air, the room ADP is equal to coil ADP and the load on the coil is equal to the load on the room. Okay. So, this is what we have to keep in mind. Okay. Normally, this simple system with 100% recirculated air is not practical. That means, we always have to have some amount of outdoor air because ventilation is required. Okay. So, but this is taken first because it is simple and rest of the systems can be developed from this system. Okay. So, now let us look at the system with outdoor air for ventilation. So, as I have already explained, in actual air conditioning system, some amount of outdoor air or fresh air is required to take care of the ventilation requirements. The required outdoor air for ventilation purposes is known from the occupancy data and the type of the building. For example, hospitals. First of all, why do we require outdoor air? As I have already told, we require it for ventilation purpose. That means, there are a large number of people inside the conditioned space. So, gradually the oxygen concentration reduces because of the respiration process, right, because we breathe in oxygen and we breathe out carbon dioxide. Okay. So, after some time the oxygen level may drop. Okay. So, this requires a continuous supply of fresh air to take care of the oxygen requirements. More importantly, it is found that the outdoor air is required to dilute the odors, okay, because people continuously emit body odors. So, that will affect the quality of the indoor air. Okay. So, you have to continuously add some fresh air which will dilute the odors. Okay. So, in all actual systems fresh air is required, right. Now, how much fresh air is required depends upon how many people are there, for example, in the conditioned space. Okay. Obviously, more the number of the people in the conditioned space, higher will be the amount of ventilation air required. There are several standards which specify what should be the ventilation air required per person per second. Okay. So many liters per person per second. Again, this also depends upon the applications. For example, in some applications the ventilation requirements may be high. For example, in areas where there is heavy smoking, okay, then to dilute the odors of the smoke, you have to supply more amount of fresh air. That means the required ventilation will be more. Also required ventilation will be more in areas like hospitals and all, where the purity of air is very, very important. Okay. In hospitals and all, in some cases all the air is thrown out and you continuously take 100% fresh air. Okay. So, what I am trying to say is the ventilation requirement depends upon all this data, okay, the occupancy data and the type of the building, etc. Okay. Generally, this kind of data is available before we design the air conditioning system, okay, because we know what is the occupancy and we know for what purpose the building is being used. Okay, so we can estimate the ventilation requirement at the beginning itself, right. So as I said, normally either the quantity of outdoor air required is specified in absolute values, or it is specified as a fraction of the recirculated air. Okay, whatever be this thing, we know how much is required. Okay, so let us take a simple case first. The case 1 is where the bypass factor of the coil is 0. That means we are talking about a perfect coil. So from the loop, okay, first let me show the system and then explain the working principle. So if you compare this with the earlier one, we did not, in the earlier system we did not have this arm. Okay, it was a 100% closed system, the same air is being recirculated. But in this system you find that some amount of air is continuously thrown out, and this is what is known as exhaust air, and some amount of air is continuously added. This air is taken from outside, so it has higher oxygen level, or it is purified and supplied. Okay, and if you look at the mass balance, you find that the exhaust air mass flow rate is always equal to outdoor air mass flow rate. Okay, because you have to ultimately balance the mass. So this outdoor air and the recirculated air, which is assumed to be at the same condition as that of the conditioned space, are mixed at this point. Okay, so what you have at this point is a mixed air. This mixed air flows through the cooling coil, it gets cooled and dehumidified, and it comes out at the condition S, and at this condition, I am sorry, this should be Ts, Ws and Hs. At this condition, it is supplied to the conditioned space, so that it can take care of the sensible and latent heat loads on the building. Okay. Now, if you draw this process on the psychrometric chart, this condition O is that of the outdoor air. Outdoor air is much hotter and humider, so you can see that this is at this point, and point I is the condition required inside the building. Okay, this is I, this is O. Okay, and at this point, this outdoor air and the inside air are mixed, and let us say that the resultant mixed condition M is here, and we have discussed this earlier. The resultant condition will be lying on a line joining these 2 points, and the exact location of the point depends upon the ratio of MO to M recirculated. Okay, depending upon that, this point will be varying. Let us for the time being assume that this point lies at this point. So at this point, it enters the cooling coil, and as the air flows through the cooling coil, it undergoes cooling and dehumidification, so its temperature drops and its humidity also drops. Okay, so this is the humidity drop and this is the temperature drop. Okay, since this is the case with of zero bypass factor, you find that the exit condition S coincides with the apparatus dew point of the coil. Okay, so the exit condition is somewhere here. Okay, so the psychrometric on the psychrometric chart, the process looks like this. Okay, so outdoor air is mixed, outdoor and indoor airs are mixed, then this mixed air flows to the cooling coil. So process MS is what happens in the cooling coil. Okay, and at this point it enters into the conditioned space. So process SI is what happens in the conditioned space. Right. So again from the room loads and inside condition, the process line is drawn. So we can draw the, since we are assuming that we know these sensible and latent heat loads, let us say that we know these loads, so we can find out the RSHF. Once you find the RSHF, you can draw this RSHF line, because we know the point I. Okay, so you know the slope of this line and you know this point, so you can draw this line. Where this line intersects the saturation curve, that is your coil ADP, and for zero bypass factors, that is also the supply air temperature. Okay, so that means we also know this temperature from this point. Okay, and once you know this temperature, then we can find out the mass flow rate of air. Okay, MS. How do you find the mass flow rate of air? From energy balance for sensible heat portion, we have seen that mass flow rate of air is nothing but CPM into Ti minus Ts, QSR divided by CPM into Ti minus Ts. Everything is known to us, QSR is known, CPM is known, Ti is known, Ts is known. So we can find out the mass flow rate of supply air. Once we know the mass flow rate of the supply air, then again performing latent cooling load balance and the total cooling load balance, we can find out the supply air humidity ratio and supply air enthalpy. Okay, so we can fix the state of the air. Okay, and that in fact for this simple case, once you locate this point, you can directly read these values from the psychrometric chart. Okay. So, okay, this is already explained to you. And from mass balance of air, that means at this point, if you do the mass balance, at this point, if you are doing the mass balance, you find that m dot O plus m dot recirculated is equal to m dot S. Okay, so because the mass is entering like this, mass is coming from this side and it is getting mixed, and the total mixed air is going in this direction, where m subscript RC is the recirculated air flow rate and m subscript O is the outdoor air flow rate. Okay, since either m subscript O or the ratio MO by MRC are specified, one can calculate the amount of recirculated air. Okay, because we have calculated this, and from ventilation requirements we know this. So, you can calculate what is the recirculated air, and the amount of air exhausted from the system is equal to the amount of outdoor air, as I have already explained. So, now we have to find out the coil loads from energy balance across the cooling coil. Okay, that means now you have to perform energy balance across the cooling coil. That means let us say take a control volume across the cooling coil and apply energy balance across the cooling coil. Energy balance means you can write an energy balance equation for the sensible heat load only. Okay, that means Q sensible of the coil, that is equal to mass flow rate of supply air into Cp of the supply air into the temperature difference. Temperature difference is nothing but inlet temperature minus outlet temperature. Inlet temperature is Tm, outlet temperature is Ts. So, this multiplied by Tm minus Ts. Okay. Similarly, you can write an equation for the latent load, and you can also write an equation for the total load. So, if you do that, then you will find that for the coil, these are the different loads. This is the sensible load, this is the latent load, and this is the total load. Okay. And here, as I have already explained to you, M refers to the mixing condition, which is the result of mixing of the recirculated air with outdoor air. And applying mass and energy balance to the mixing process. So, this we have seen in the earlier lectures, how to apply the when two air streams are mixed, how do we find the exit condition? Okay. So, here we have mixing of two air streams. Okay. So, this one air stream and this second air stream, these two air streams are getting mixed. This air stream is coming from the conditioned space at the condition same as that of the space, and this air stream is coming from outdoor. Okay, that means this one and this one, both are getting mixed, and we would like to find out what should be this point. Okay, where should be this point? So, that is obtained by again applying mass and energy balance across this point. Okay, so from mass and energy balance across the point, you can easily show that the ratio of outdoor air divided by the supply air, that is MO divided by MS, is equal to Wm minus Wi by Wo minus Wi, where Wm is the humidity ratio of the mixed air and Wi is the humidity ratio of the conditioned space, Wo is the humidity ratio of the outdoor air. This is also equal to the enthalpy ratios. Okay. And if you are assuming that the specific heat remains constant, this is also approximately equal to the temperature ratios. Okay. Since we know this, we also know this, we know this, so you can find out Wm. Similarly, in this equation we know Hi, we know Ho, so we can find out Hm. Similarly, we know Ti, To, so you can find out Tm using this equation. Okay. And since Mo by Ms is always greater than 0, because you are always supplying some amount of outdoor air, from the above equation it is clear that Wm will be greater than Wi. So, Hm will be greater than Hi and Tm will be greater than Ti. Okay. This implies that Ms into Hm minus Hs is always greater than Ms into Hi minus Hs. Now, what is Ms into Hm minus Hs? This is nothing but the load on the cooling coil. And what is Ms into Hi minus Hs? That is the load on the room. So, you find that whenever you are using some amount of outdoor air, the load on the cooling coil is always higher than the load on the room. Okay, load on the conditioned space. This is obvious because what you are doing by adding outdoor air is you are adding some energy to the system, and at the same time you are throwing out some air which is cold and dry, I mean compared to the outdoor air. Okay, so you are throwing out some cold air and you are taking in some hot air. Okay, so you have to pay some penalty for this. So this penalty is paid at the cooling coil by the difference between the loads on the coil and the building. Okay, the difference between the cooling load on the coil and cooling load on the conditioned space can be shown to be equal to QSC minus QSR, that is equal to MO into CPM into TO minus TI. Okay, so this is the difference in the sensible cooling loads of the coil and the room, and this is the latent heat loads of the coil and the room, and this is the total heat load. So this you find that is proportional to the amount of outdoor air added, and it is also proportional to the temperature difference or humidity ratio difference or enthalpy difference. Okay. So from the above equation it is clear that the difference between cooling coil and conditioned space increases as the amount of outdoor air increases. So you can see that as MO increases, this difference also increases, or as the outdoor air becomes hotter and more humid. Okay. This is the reason why in air conditioned buildings and all, normally for example air conditioned theatres and all, they do not allow you to smoke. Okay, because once people smoke inside the conditioned space, then the required outdoor air will be more. Okay, you have to supply more amount of ventilated air or outdoor air to take care of the odors because of the smoke. Okay, so more amount of outdoor air means more amount of load on the cooling coil. More amount of the load on the cooling coil means the cooling coil capacity has to be higher. So initial cost will be more and running cost also will be more. Okay, so smoking etc. in the conditioned space is not good from this point of view. Okay. The line joining the mixed condition M with the coil ADP is the process line undergone by the air as it flows to the cooling coil. The slope of this line depends on the cooling coil sensible heat factor. Okay, so let me just show this thing. What I am talking about is this line. Okay, this as we know, this line is your RSHF line. This line is nothing but the process line for as the air flows to the cooling coil. Okay, process MS. Okay, this depends upon what is the ratio of sensible and latent heat loads at the coil. Okay, so you can define what is known as the coil sensible heat factor CSHF as the sensible heat load on the coil divided by total heat load on the coil. Okay, so that will give you the coil sensible heat factor, and then you can find out the slope of this line. Slope of this coil here line as let us say that this is theta 1, let us say, then tan theta 1 is equal to 1 by 2451, we have seen this, 1 minus CSHF divided by CSHF. Okay, so this we can find out from the coil loads, so you can find out the slope of this line now. Okay, so that is what is given here. Now let us look at another case, case 2, coil bypass factor X is greater than 0. For actual cooling coils, the bypass factor will be greater than 0 as a okay, because it is not possible to have a perfect coil, so you will always have some amount of bypass factor. As a result, the air temperature at the exit of the cooling coil will be higher than the coil ADP, and the process gets modified. So when you have a bypass factor, having a finite bypass factor of the cooling coil is equivalent to saying that some amount of air, that means this amount of air comes in perfect contact with the cooling coil, and this amount of air is completely bypassing the cooling coil. Okay, so ultimately the mixed condition you get here is a result of the air which is completely bypassing this, and the amount of air that is completely in contact with the cooling coil. Okay, so again if you apply the mixing rule, then you can find out what is the mixed condition. Okay, so this is a system with bypass factor greater than 0. So what is the change in the psychrometric chart? You find that on the psychrometric chart there is a difference. Okay, since bypass factor is greater than 0, you find that the exit condition of air from the cooling coil Ts is greater than T ADP, because from the definition of bypass factor we know that X is equal to Ts minus T ADP divided by Tm minus T ADP. Okay, M is the inlet condition to the cooling coil. This is greater than 0, right? That means Ts has to be greater than T ADP. Okay. So, when x is greater than 0, the room ADP will be different from the coil ADP, that is also clear from here. You can see that the coil ADP is this temperature, room ADP is somewhere here, where this is your room sensible heat factor line, okay. This is your coil sensible heat factor line. So, the point where this line intersects the saturation curve is your coil ADP, and the point where the room sensible heat factor line intersects the 100% saturation curve, somewhere here let us say, this is your room ADP, okay. This is your room ADP, and they are not same here, okay. Normally in actual systems, either the supply temperature Ts or the temperature rise of air as it flows through the conditioned space Ti minus Ts will be specified, okay. Based on some other criteria which we will discuss little later, generally in these values are specified, either the supply temperature or what is the temperature rise of the air as it flows through the conditioned space, that is Ti minus Ts, okay. These values are specified, not the exact values will be specified, but the range is given, okay. For example, it is generally specified that Ti minus Ts should be between say 8 to 15 degrees, okay. So, you can choose any value between 8 to 15, okay. So, since the supply temperature is specified, one can calculate the required supply air flow rate and supply conditions, okay. So, what I am saying is we know this temperature is known to us, this temperature is known to us. We also know load on the sensible load on the building. So, we have seen this equation before, this is equal to Ti minus Ts. So, Ts is specified, Ti is known to us, Cpm is known to us, this is known. So, you can find out what is Ms. Similarly, we have seen the other equations, sensible heat load of this thing is Hfg into Wi minus Ws. So, Ms is calculated, Hfg is known to us, Ws is known to us, so Ws can be obtained. So, you can fix this condition also, okay. One can draw the line Is from the known values of supply temperature and RSHF. The intersection of this line, as I have already told you, with the saturation curve gives the room ADP. Condition of air after mixing, that is point M, is obtained from known values of Ms and M0 using mixing rule, okay. So, this again I have explained this condition, okay, using the mixing rule, because we know the air flow rates and we also know these two conditions. So, we can find out this point. Joining points M and S gives the process line of air as it flows through the cooling coil. The intersection of this line with the saturation curve gives the coil ADP. If the coil ADP and coil bypass factor are given instead of the supply air temperature, then a trial and error method has to be employed to obtain the supply air condition, okay. So, instead of specifying the supply air temperature, if the coil bypass factor is given, then we have to go for a trial and error method, okay, because all that we can do is to find the room ADP and draw the room sensible heat factor line, okay. We do not know what is the supply air temperature, okay, but the coil ADP is specified, coil bypass factor is specified, okay. So, you can draw the coil ADP or locate the coil ADP on the psychrometric chart, and using the bypass factor and using a trial and error method, we can fix the supply condition, okay. The system described so far is adequate for applications where the sensible heat load is dominant, that means your room sensible heat factor is greater than about 0.75. When the latent load on the building is high, due either to high outside humidity or due to large ventilation requirements, for example in hospitals, or due to high internal latent heat loads, for example your conditioned space consists of a kitchen or a laundry, then the simple system discussed above leads to very low coil ADP, okay. So, whatever system we have been discussing so far, that is fine as long as your sensible load is more than 3 times that of the latent load on the building, that means your room sensible heat factor is greater than about 0.75, which is normally the case, but there are some special cases where the latent load on the building could be quite high, okay. Some of the examples are where the outside conditions are highly humid, okay, for example in coastal areas, or where there is lot of internal latent heat load, okay. As I said, for example you have a laundry or a kitchen inside the conditioned space, a lot of moisture is continuously added, okay. So, for these conditions you find that the room sensible heat factor will be low because the latent heat load is high, okay. Low means it could be lower than 0.6 or so, okay. For these special circumstances, if you are using the simple system, you find that the required coil ADP, that means required surface temperature of the coil, will be very low. Now, the surface temperature of the coil is connected to the evaporator temperature of the system. Okay. Since it is connected to the evaporator temperature of the system refrigerant system has to be operated at very low evaporator temperature. Okay. And as you know, when you operate the refrigerant system at low evaporator temperature, the COP of the system reduces. Okay. That means your running cost of the system goes up. Okay. So, normally for high latent heat load application, some modifications are done so that you get reasonably high COP of the refrigerant system. Okay. So, one of the modifications is what is known as a system with reheat coil. Okay. So, a low coil apparatus dew point indicates operation of the refrigerant system at low evaporator temperatures. This is all repetition of whatever I have said. Operating the system at low evaporator temperatures decreases the COP of the refrigerant system. Hence, a reheat coil is sometimes used so that the cooling coil can be operated at relatively high ADP, and at the same time the high latent load can also be taken care of. Okay. I will explain this system shortly. In a system with reheat coil, air is first cooled and dehumidified in the cooling coil and is then reheated sensibly to the required supply temperature Ts using the reheat coil. Okay. So, that means first let me explain the system hardware. So, again you have the condition space here where we require Ti and Wi, and this is supply state. We require this much amount of air flow rate at this temperature and this humidity and this enthalpy. At this condition, this is supplied to the condition space, and again we have the sensible heat load on the room, latent heat load on the room. Okay. So, we have the cooling coil here. In addition to the cooling coil, we have also a heating coil. Okay. So, this is a heating coil. Okay. So, first what is done here is the air is first cooled and dehumidified in the cooling coil, then it is sensibly heated in the reheat coil. Okay. So, first you cool the air and remove the moisture in this process, that means it is a cooling and dehumidification process, and once you remove the moisture, then what you do is you sensibly heat the air by passing it through the reheat coil, so that you get the required supply air condition. Okay. So, this is shown on the psychrometric chart like this. Okay, let us begin at this process. We have the indoor air and outdoor air, both are mixed and we get a mixed condition. This mixed condition flows through the cooling coil, cooling and dehumidification coil. Okay, this is your cooling and dehumidification coil. In this process, you can see that the required amount of moisture is extracted. Okay, so this is the amount of moisture to be taken out. So, that is achieved in this process, but you find that this temperature or this point does not lie on the RSHF line. Okay, if this is your RSHF line, and this RSHF will be quite low because of the high latent load, let us say this is less than 0.6. Okay, since this point does not lie on this line, if you leave air at this condition to the conditioned space, it cannot take the required amount of sensible and latent heat loads. Okay, so somehow you have to bring this point onto the room sensible heat factor line. Okay, so for that purpose, what is done is at this point air flows through the reheat coil, and in the reheat coil it is sensibly heated. Okay, so in the reheat coil the temperature increases from Tc to Ts, so that the point S lies on the room sensible heat factor line, so that it can take care of the latent and sensible heat loads. Okay, since it is a sensible process, Tc will be lower than Ts. Okay, and Wc will be equal to Ws. Okay, so no change in the humidity ratio. And we have to find out now the capacity of the reheat coil. The capacity of the reheat coil is obtained from energy balance across the coil. Very simple. All that you have to do is take this as a control volume and perform the energy balance. Okay, so from that you find that only sensible heat transfer is taking place. So then reheat coil QR is equal to mass flow rate of the supply air into specific heat of the air multiplied by the temperature difference Ts minus Tc. Okay. So Q reheat is given by Ms into Hs minus Hc. Since this is a pure sensible heat transfer process, Hs minus Hc is written as Cpm into Ts minus Tc. Okay. So with reheat the system operates at higher coil ADP, that means you can expect high COP of the refrigerant system. how the required mass flow rate of air increases. Okay. So, the benefit of the reheat coil is that you can operate your refrigerant system at a higher evaporator temperature, but there is also a disadvantage, because first disadvantage, you are unnecessarily cooling the air to a lower temperature and then you are heating it. So, energy is required first for cooling and energy is also required for heating. Okay. It is actually wasteful use of energy. Second thing is that because of this reheating process, the temperature difference Ti minus Ts reduces. Okay. Once Ti minus Ts reduces, the required amount of supply air increases. These are the two disadvantages of the reheat coil. Okay. And the benefit is a higher COP. So, ultimately in an actual system, one has to perform calculations and see whether reheat coil is justified or not. Okay. And if possible, energy for reheat can be obtained from a waste heat source such as condenser. Okay. That means instead of using, let us say, an electrical heater for the reheat coil, you can also use a waste heat source. Okay. One of the waste heat sources is the heat rejected at the condenser. Okay. If it is possible, you can use that heat for heating the air in the reheat coil. Okay. That is how you can reduce the energy consumption. Okay. So, at this point I stop it and let us conclude what we have learned in this lecture. In this lecture, the following topics are discussed: selection of outdoor design conditions, psychrometry of summer air conditioning systems with and without outdoor air, and systems with reheat. Okay, we will continue this lecture in the next class. Okay, thank you.